Hello, everyone. Welcome to a Solar Saturday sun streaming session from the Naperville Astronomical Association here in Northern Illinois. We have a lovely sunny day here. I'm Drew Carhart. I'm the current club president, and I'm being joined today by Jim Irwin in Romeoville and Frank Lecar in Plainfield, Illinois, who are both of their telescopes set up to provide us with some live viewing of the sun today. And you may have joined us back in June, the last time we did a solar session, a daytime session. And I'm not going to repeat everything I said. We put all of our videos of our streaming events now up on YouTube, so feel free to go and look at our channel there and see what we're doing. But the principles I will cover of what we're going to visit today. So I'm going to share a picture of the sun to you, with you. There we go. So we have the a cutaway diagram of what our star, the sun, looks like, being provided to us by NASA, wonderful NASA here. So the sun is a star. It's the closest star to us, of course, and it's the only one that we can really see the details on. So it's an amazing thing for astronomers to study, and even for amateur astronomers. I do want to point out, we do have, if you're watching us on Facebook, theoretically, I am able to see the feed from Facebook. If you have any questions you want to post, I will pass them along to Jim or Frank, or try to answer them myself. As I was saying, the closest star to us, and the only one who can see in details. This cutaway view shows the inside that we never see, but what we're going to be looking at today is two different layers of the outer part of the sun, what we would call the surface of the sun. Of course, the sun is a ball of gas, so it doesn't have a hard surface like a planet like the Earth does. But the main surface that we will be looking at first, which is what you see when you look up at the sky at that big bright white disk, is what's called the photosphere. So in this diagram of the cutaway, it's this upper right quadrant here. So this sort of orangish area here is that face that we see. And the main feature on that face are showing here are sunspots. We actually have some sunspots. It's one of the reasons why we decided to do another solar streaming session. When we did this earlier in the year, there weren't any sunspots to speak of on the face of the sun, so there wasn't anything to show you there. The face of the sun itself that we're looking at, that photosphere, is very hot, of course. It's shining because it's hot. It's about 10,000 degrees Fahrenheit in temperature. And sunspots are simply cooler patches on the sun. They're a little bit cooler. They're a couple thousand degrees cooler. They may be a little over 7,000 degrees, up to about 8,000 degrees in temperature. So they're still very hot. They just don't shine as brightly because they're not as hot as the rest of the surface around them. They're caused by the magnetic lines of the sun. So the sun has a strong magnetic field, just like a bar magnet. It has loops coming out of it, out of the poles that reconnect to the other side. But in the sun, those magnetic field lines get tangled up as the sun rotates, and it goes through phases. It goes through a cycle of a period of having very few sunspots on it, which we're just coming out of now, to a peak where there's a lot of sunspots, and then back down to a trough where there are a few sunspots again. And again, that's caused by the magnetic field lines of the sun getting more and more tangled up, and then kind of straightening out and getting more and more tangled up. And as they get tangled up, where they push through the surface of the sun, they can actually slow down the transmission of the heat from the core of the sun out to that bright face of the sun. So you get little cooler spots. So we'll see that today. Up above that bright surface that we normally associate with the face of the sun, there's a layer of atmosphere, which is actually a little bit cooler right above it there. We'll be looking at that The only way we can see that is to focus our telescopes only on the wavelength of hydrogen light that that atmosphere emits. If you ever get the fortunate chance to see a total eclipse of the sun, you get moments where in craters around the edge of the moon, you will only see that bright atmosphere of the sun, and it's a very bright red color. It's called the chromosphere. It gets the name chromosphere from the color of it. And we can take a telescope that is filtered to only look at that red wavelength of light, and so it ends up blocking most of the bright light from the face of the sun and lets us see that atmosphere. We'll be doing that. And then today we're adding in a third color of light. It's a line, an emission line from the element calcium. And there's actually calcium, just like in your milk or in your bones. The atmosphere of the sun has some calcium in it. And in its light, we tend to see the magnetic lines of the face of the sun very magnified, because the calcium light highlights where these twisted magnetic lines are pushing through the atmosphere of the sun. So it's actually looking on just a little above the hydrogen light, where we will see prominences coming off the edge of the sun and into this, again, a higher and hotter area of atmosphere of the sun where we're seeing magnetic lines. So without further ado, we'll go to a live view of the sun in white light. So basically, Jim's got a telescope. I'm going to unshare. Jim's got a telescope that has a filter on it that allows him to safely look at the sun through the telescope by blocking out almost all of the sunlight before it even gets to the front lens of the telescope. It blocks out all but a very tiny percentage to make it safe. If he looked directly through his telescope to his eye, the sun then would look about as bright as the full moon does, and not deathly bright and burning his eye instantly like it would without a filter on the telescope. So Jim, do you want to tell us a little bit more about what you've got there?
Yeah, so this is just it's a small 80 millimeter scope with just what we call a white light filter over it. And then, as you can see, this is the main big sunspot, and there's a smaller sunspot here. You can see the darker area. This actually looks a lot better with your real eye than with the telescope, because your eye can kind of pick up different variations, I guess. The camera has to be set to a certain shutter speed, so that kind of limits. It makes the camera a little more of a limiting factor here, but you can see that there's a darker area of that sunspot, and then there's a lighter area around it. And I think when we see Frank's camera later, that'll come into a little more detail, and even in the H-alpha filter, this will show up a little bit better because I'm zoomed in a little bit more on that area.
I think this particular sunspot, again, it's about the biggest one that's appeared so far in this new solar cycle, this new grouping of sunspots coming out that we've seen trickling in this year. The darkest part of that, the center of that sunspot, which is called the umbra, surrounded by the penumbra, which is the lighter circle around it. But that umbra of this particular sunspot is right about the size of the Earth on the nose as far as diameter across. So you could take a little globe of Earth and put it there. That's about the width of our whole planet, is that darkest part of that black blotch on the sun there. This sunspot has been changing. Sunspots vary from day to day, actually. Sometimes they'll grow, sometimes they'll sprout into larger groups or split apart. Other times they'll shrink and fade away, so they're very unpredictable. But if you watch them over days of time, I'll share it with you a little bit in a website where you can see satellite views of the sun too. And if you go to some of those resources, they'll show you movies of them changing over recent days. I want to
just a fun fact that I'd like, if there's any kids watching, that I like telling people. So from here to here, this is about, I think it's 108 Earths.
Sounds good. Yeah.
And then, you know, obviously it's 108 Earths that way, and then it's 108 Earths that way, you know, deep. So it makes it like 100 and, what's the size of the sun?
Oh, in diameter?
Yeah.
Oh, you know, I'm terrible with numbers.
108 million miles across. Is that
something like? Well, no, it would be less than that. It'd be half that. So yeah, but it's a lot. So it's a lot.
Well, you could fit over 1 million Earths inside the sun.
That's right. If you hollowed it out and poured them in. So again, that little dot there, that little black dot on the face of the sun there is about the size of Earth. Is pretty amazing. Why don't we go back, and I will show some other current images while you flip over to seeing.
Okay, I'm going to stop sharing.
While you flip over to seeing the hydrogen alpha view. And so I'm going to share this window again. So this is one of the home pages of a satellite that is up in Earth orbit, and it's watching the sun all the time. And so we have the SDO satellite and the atmospheric imaging assembly. Anyway, these are images of the sun taken within the past hour, always, sometimes within the past minutes, usually. And what we're seeing here in this little array across the screen here are different wavelengths of light, just like we've been talking about. So if I go over to this N1 and click on CONT, stands for continuity, which is just basically the white light picture. Here's a image from, again, within the hour, if you see the date, the time out there, and of the sun, and showing you the sunspot group that you could see in Jim's telescope, but a little more clearly here, and you can see all of the little daughter sunspots around it. So sunspots often come in families or in clusters like this. You've got this other one nearby here. So we're going to be zooming in a little bit more on this area. So again, this is basically a white light view. What we'll tend to see is the disk of the sun. We'll see it looking brighter in the center and dimmer off to the edge. That's called limb darkening, and it's a real effect. Off toward the edge is where we also see in white light this feature where you can see a little bit up in this upper corner here, or a little down here, where looks like there's whitish squiggly lines on the face of the sun. Those are called faculae, and they're the opposite of sunspots. They're brighter areas. Instead of being in spots, they tend to look more like squiggly lines oftentimes. They're usually found around sunspots, but they tend to blend into the surface when we're looking straight down on them like this around this big group. You tend to see them better in white light along the edge. Those are the feature that Frank's telescope, which we'll look at in a little while, really accentuates, is where there are these brighter areas where the magnetic lines are actually twisting to allow more heat flow out through the face of the sun. So these other images on this page are all different wavelengths of light that the satellite is constantly taking pictures in to once again bring out different features. What the different wavelengths show is different elements and different temperatures. So different features will be highlighted um, in the different views. So the sun is being studied all the time, both from earthbound telescopes and from a couple of spacebound platforms telescopes. And this is something you can easily find online if you just use your favorite search engine and look for current solar images. You will find a lot of views. I'm going to switch to this set of telescopes, the GONG network, which is an interesting acronym, is telescopes located all around the world. You'll see India, and you'll see England, and you'll see California and Hawaii and South America here. So these are earthbound telescopes that are viewing in this hydrogen alpha light, which is what we're going to switch to Jim's view of. And are you ready to go, Jim, with that?
Yes.
You are. Okay, then I will stop sharing and let you take over.
So the first thing I want to talk about here is this this stuff happening at the edge, this waviness around here. That's not the sun. The sun is, the movements of the sun are much slower because it's such a huge object. This is heat waves coming off of my neighbor's house that's being detected here. When they take a still image of the sun, they don't have all these heat waves and stuff to deal with. So this is in hydrogen alpha. This is an 80 millimeter telescope that has a Daystar filter on it. So it's a nighttime telescope that just gets modified for daytime viewing. Now what I'm going to show you here is if I change the exposure and overexpose this, you will see these prominences come up on the edge. So here's a really nice one. It makes this arch. There's some down here, some small ones here. These are, I'm sure the Earth could fit through that loop there. I don't know positively how big it is, but everything on the sun is huge, so I would be pretty confident that the sun could fit through that. These arches are really great. I think the best way to explain is this is going on these magnetic lines, and this is different than a solar flare. But I've heard them talk about it, that it's like you take a bunch of rubber bands and you twist them and twist them and twist them, and eventually sometimes these solar prominences snap and it'll blow all this material off into space. But typically what happens is this is more like a belch, more like a burp. A little bit of gas comes out of the planet, and then after a few days, sometimes a few hours, sometimes a few days, it gets sucked back into the planet. So it's just a little bit of a gas being emitted along these magnetic lines. If I back the exposure back down, or take the exposure down, you see a lot more of the surface detail. So these things here are called filaments. I think there's one there. These are the same thing as a solar prominence, but it's things when they're facing us. So there's still, instead of an arch being out here, it's on the sun. So sometimes they look like little snakes or little worms on the sun, but that's the same features that we're seeing on the edge that are facing us. So those are called filaments. Oops. And then I'm gonna move the telescope over a little bit, and here we see these sunspots that we were seeing earlier. So we're a little more zoomed in, and you can see all this other activity that's happening around it down here too. I do see one sunspot there, but the view I'm in, I'm still not going to see all the sunspots that I think Frank's going to see from his view. Or if we were more zoomed in on a white light filter, you'd see, if you remember earlier, there was kind of a whole trail of sunspots through there. But I'm not seeing those in this specific this specific filter. And I'm going to come to the other side, and I'm going to turn this, overexpose this again, and we have a whole bunch of prominences happening on this side too. And there is one that's making a little bit of a loop here. But there's a pretty big one here. That looks like a small loop there. I mean, really, this whole area is pretty active right now. And I think that's all the activity. Let me walk along the edge so you can see some small stuff. Oh, there's one. There's one up there. So I mean, all along the edge, there. Oops. If I can drive my telescope. These things can happen anywhere along the telescope or along the edge of the sun. Drew, is there anything specifically you wanted to talk about? I can back the.
I can share the this South American image, which, to be fair, will look more like what you see through your telescope than what the video camera sees through the telescope. But actually, you've got the exact same orientation that they do. You're right on the nose. You've got your camera rotated right. So.
I do have a little bit of dirt, and I apologize for that. I have a little bit of dirt on the. That's just dirt. So if I bump the telescope, that doesn't move.
That's a speck of dust which you could barely see looking at it on James' camera. Is what that is.
Yeah, my camera picks it up. Your eye wouldn't notice that at all, but my camera totally makes that. It looks like I got it specked down there too. They don't move.
No.
Okay, do you want me to stop sharing?
Oh, that works.
Okay.
You can move on. So let me share back again to this screen here.
One other thing I want to point out. Again, the limitation of the camera, I had to adjust the exposure, but you're looking at this with your real eye. Your eye can kind of handle both those exposures at the same time. So your eye would be able to see surface detail and prominences when looking at the sun, where the camera, you have to kind of pick one or the other. So a lot of times these images like Drew's showing, they've actually taken two exposures and they put them on top of each other. So they take an exposure of surface detail, and then they take an exposure of the prominences, the edge detail, and they just line those up. So it looks like it's one image, but typically it's a couple images that are stacked together. But your eye can do that automatically, where
that's exactly correct.
Where the camera can't
and
quite
even
do that.
Even the amount of detail, looking through Jim's telescope, you would see more detail than this camera picked up even, because again, it's amazing what the eye can do, no matter how cool cameras are these days. But again, he started us out here. So this picture was taken a couple minutes ago. He started us down here with this big group and that loop that he showed us, and then circled around to this lower right-hand quadrant where there's this whole little forest of activity, and then he showed little things popping up along the edges. So again, he's showing through his telescope live what this professional survey telescope is seeing. And again, you'll have to take my word for it, it's not Jim's. The image through his telescope without the camera, just looking with his eye, would be considerably more detailed than this. One of the amazing things of looking at in hydrogen alpha like this is these jets of gas coming off the sun change in their shape and in their orientation on the matter of minutes. Actually, you can look at spikes and arches like this and look at them 10 minutes later and see that they've moved. So you actually see the dynamic face of the sun, which is quite amazing. So Frank,
there's YouTube videos where people will speed that up, because you can't stare at something for 10 minutes and notice that it changed. But if they speed it up in a YouTube video, you actually see that it's almost like the flame of a candle that's dancing around and actually whatever it wants to do.
I've got one I can actually share up on the other screen. We can end up with that. Frank, are you ready to go? You'll have to turn your microphone back on, Frank. You're muted. So,
there we go. Sorry about that.
Spotlight him, Drew.
Yeah. Okay. Yeah, we've been tracking here and we're ready to go. Do we have your full screen there? There we are. Okay. Now this, I should explain, this is a view of the sun through a K-line calcium filter on my 5-inch refractor. The K-line, the calcium light, is at a different altitude than the hydrogen alpha that Jim was showing us. It's actually a little, well, it's actually different, various layers. Most of it, though, is a little lower in the chromosphere than the hydrogen alpha. You can see the spots there, and if you look very carefully, you can also see the faculae or plages, to use the French word. Plage is French for beach. And they do look like little beachy area, a beach around a tropical island, you might say. Notice the sunspots are very, very dark here in the calcium view. That is because the calcium ions are really susceptible to magnetic fields. And so they really go crazy when they're in a strong magnetic field like this. I'll change the exposure slightly and you'll be able to see some of the penumbra. There's darker, you can see the faculae, and now you can start to see the umbra of the sunspot itself. There are quite a few little spots on there. Now, wherever you see faculae, that's a good indication that another sunspot may be erupting. And I noticed on Jim's view and on mine a little earlier that there is an edge. There's one coming around the edge of the sun. I'll move the telescope so I think we might be able to see where that is. Again, you can see some little faculae coming into view. And we'll go up here. Okay, now right about in just to the, I'll put it in the center more or less. I'll remove the crosshairs. I'm sorry about that. I normally like to have crosshairs. You see that little whitish area on the edge of the sun. Oh, those are additional faculae and a new sunspot's probably developing there. So we'll have to watch. That's just coming around the edge. So we'll have to watch that area. We'll bring the main cluster into view again. And as Drew mentioned too, this is one of the biggest sunspots we've had in, I would say, a couple of years, wouldn't you, Drew? I mean, this is huge. And again, you can see there are smaller sunspots developing. Now, only twice in my life have I been lucky enough to see a solar flare develop while I was watching the sunspot. If you do have a solar telescope, even a white light solar telescope, you can see solar flares if you're lucky. Right in the middle of the sunspot, a white little spot will suddenly appear and flare over a period of about 15 minutes. If you see one of those, it's quite spectacular. It's much brighter than the rest of the air, brighter rather than the surface of the sun itself. Again, we have the umbra and the penumbra here. These are probably only about as big as the state of Texas, but what are you going to do? Now I can zoom in a little bit here. Let's see. Okay. You can sort of see the granulation of the sun there. Now, part of the movement is due to the seeing. The seeing isn't all that great today, but you can still see some of the granulation of the sun. Each one of those granules is, again, the size of a small state here in the US. I'm going to zoom out again a bit. And yeah, we're looking again through a filter. Now, if you want, I have both hydrogen alpha and the calcium line. The hydrogen alpha, generally speaking, is more interesting, I would say. But the calcium line filters are rather pricey. And so I have one made by the Bader Planetarium in Germany. And it can be used on any telescope. You do not need a special telescope to do it. And you can only use it for imaging. You cannot use this for visual work. One of the main reasons is you can't see anything through this filter. The calcium line is right around the edge of the violet and ultraviolet. If you look through the telescope, you might, if you have good eyes, see a pale purple or violet image. But that's sort of dangerous because this lets in most of the ultraviolet light, and looking at a telescope with ultraviolet coming through it is not a good idea. But you can use it for photography, for imaging. I'm using a Titan, an Attic Titan Astro video camera here to get these. And I'm shooting at 1/7,000th of a second, believe it or not, but it's a bright image. So anything to add to that, Drew or Jim, in that case?
No, I think you covered it well. Jim, did you have anything you wanted to switch back to image-wise?
I don't have anything
Okay.
different from what.
Nothing new has appeared in your on the sun. So I've got a couple of professional things that I could share just briefly to close out with. Frank mentioned the granulation on the surface of the sun. And again, you can see it to some extent in his image that's up right now. The surface of the sun does not look smooth like a blank painted wall or a ping pong ball or something. It looks pebbled like the surface of an orange, more like. Let's see, Frank, are you still sharing? No.
Yeah, am I still am? Yes.
Yes, you're still sharing.
Can you see that new sunspot coming off the edge here?
Oh yeah.
Yeah, around the just a little below 9 o'clock there. Yes, there is one little dark guy there. I noticed in white light. So,
let me adjust the exposure on that a little bit. See if we can get him brighter. Wait a minute. There he is. Yep. There's another one coming around the edge.
Yeah.
I'm just sort of scanning all around the sun to see what else is visible. We've hit the main sunspots, of course, but again, you can see occasional faculae. Nothing much on this part of the sun. This is, I think we're looking at the northern part of the sun here. The image is upside down, of course.
I was actually wondering about that area, Frank. I'm going to share my screen real quick and show what it looks like in H alpha.
Okay.
You can tell
the new spot we're looking at?
Yeah, that new sunspot.
Okay.
So you can tell, a little bit of astronomy is seeing things that aren't necessarily there sometimes, but you can tell that there's something there. I can't quite tell what it is, but I can tell that it's different than the rest of the surface detail. There's a little bit of a lighter section. So I think what Frank showed was about right there. There's a new sunspot.
Yeah, right here. Here we come. Yeah. Yeah.
I think that's the same area that
Yeah. Yeah.
are. If your cameras are angled differently, you get a little different view of the sun.
I will zoom in on that a bit. There we go. And I'll try a different exposure too. That's darker. Let's get a little lighter. Yep. There it is. And again, the faculae are are still visible there.
And you have another one that's actually up at about 10 o'clock. There is actually a little black dot up there and faculae around it, about the same distance from the limb. I'm just looking at the continuing the white light view online and the H alpha view, but
I'll track to the other side here, and we'll see if what's you say it's
more like 10 o'clock up at the upper left. So
from my
that one down there is yes, that's definitely a sunspot. That was center on the sun about 5 days ago, and that one's leaving. The one
that one's leaving. Okay.
So no, the up and to the left is
up and to the left. Okay. Yeah. And the other
left.
Further left. Okay, hold on.
It'll be pretty close to. There you go.
Yeah. Okay.
So there's actually a little black dot at the front edge of that in white light, but you're just seeing the faculae around it. So,
yeah, I can't see the spot. I can only see the faculae. Yeah. Yeah.
Yeah. So, folks out there watching, again, solar observing can be a very interesting part of amateur astronomy. You think of this astronomy being nighttime, but this is daytime astronomy, and you can start out with it. The most basic way is to do what's called solar projection. You can do with a regular telescope. It's kind of a very crude method where you let your sun turn into like a film projector and shine an image out onto a piece of white screen, a cardboard or whatever, a piece of paper. You can see some things, like once a sunspot gets about as big as this big one is that we've been looking at today, you can spot it using that. Regular nighttime telescopes can be used for solar observing if you add a precision-made, a real, genuine solar filter out in front of the telescope to block the light before it comes in. You can do white light viewing, like the white light viewing that Jim started us out with, and see a lot. And then you can also go into the more specialized things, like the viewing that Frank's been showing us, and the hydrogen alpha viewing that Jim's been showing us.
But white light fairly inexpensive too.
Right. Oh, actually, yes. We in our club, we stock for members. We do bulk purchasing of it, and we can sell you the material to make a solar filter for your telescope for a real, genuine, safe solar filter for under $10. So it's not an impossible thing to add to your collection. Obviously, you never want to observe the sun without a genuine solar filter, and you do not want to ever use the kind they used to sell with little refractor telescopes that you screwed into the eyepiece. Those inherently are not safe. You need something that's a modern, safe piece of equipment for safely looking at the sun. But a lot of us have spent many, 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 many hours staring at the sun. And again, our eyes do a much better job than our cameras are doing today for showing you things. And we have not lost a bit of our eyesight for it because we're doing it very carefully. But again, it's an interesting thing to add. I will share, again, I'm showing, hopefully, this is a space view of the sun in white light. So those things we were just looking at, here's the group that the area that Frank pointed out, coming around at this 8 o'clock position of the sun, where he was showing the faculae, where he's saying spots might be starting out. This is the group I was saying was up at 10 o'clock. There is one little black dot there, and then those faculae that we saw there. If we go to the hydrogen alpha current image, again, there's those same active areas. Again, you saw the faculae better probably actually in the calcium view and the very deep violet view, because that shows that up the best. But this, again, this texturing of the surface, I just wanted to address that again a little bit. So the sun, again, it's not a solid surface. It's not a planet. It's a ball of gas, and it's basically boiling gas. There is so much heat pouring out from the center of it that the gas is always very turbulent. A new telescope was just commissioned this year. It's just going online in Hawaii, that gives us the most amazing views that we've had yet of that boiling surface of the sun. So this is the Inouye telescope. So these are the bubbles that cause that granular effect that we see in the surface of the sun. Even with our amateur telescopes, we don't see them up close like this. And again, one of these bigger ones is like the size of the state of Texas. We've got, you know, these massive heaving bubbles of gas, which are the hot gas surging up in the center, cooling off by radiating their heat energy outward, and then their cool gas is pouring back down around the sides. So they're like fountains that are constantly going. So that's an interesting thing. I want to go last up to this screen. And this is just to show you that activity on the sun. This is from the SDO, the satellite that I was showing you the page of, but this is a time lapse of the activity going on in the sun. So you see the various prominences coming up, but especially on this, like on the edge here, you see this fountain that's growing up here. This is what we were seeing in that one group today of this arch shape. So they were following the magnetic lines. If you ever played with magnets or were shown them in grade school or as a kid and seen the iron filings, they make these loops over the magnet ends where you can see the magnetic lines. That's exactly what you're seeing here. So again, this is a matter of hours that this is sped up from, but you actually see some of this motion, not quite in this sharp detail, but you see motion like this in our amateur telescopes, and it's quite an amazing thing to follow, to watch, say over an hour's time, watch something like this change its shape and see the bright parts of it move around. You can see sometimes they'll just collapse, they'll go away. Sometimes you'll see a new one sprout up, and they make different forms. But it's quite an amazing thing to watch. Again, there's no other star that we can look at and see in this detail.
You back that up like 20 seconds, Drew, and look at that. Back that video up like 20 or 30 seconds and watch that white section over on the left. You can see some of those. It kind of spurts out.
Oh, over on the left, over here.
Yeah.
Oh, like that. There.
Yeah.
Right.
That's pretty cool.
Right.
Yeah.
Yeah, you actually see. So what you're doing here is looking down on something like that over here on this edge. Here's looking down from the top. So all of this jetting and things is coming toward you rather than you're seeing it in profile like this on the edge. So, yeah, again, it's like that there. Yes, it's amazing to watch. So I think it's about time for us to wrap up. Let me come back onto the screen here. I think I came back on the screen. I don't see any questions in the comments section, so nothing to pass along to from that way. Jim or Frank, did you have anything you wanted to say in closing?
No, let's try doing this again maybe in about another month. I suspect now that that the solar minimum is obviously over, we should have some really interesting days of solar observing in the next couple of months, I think.
Agreed. And we're going to keep on playing with our equipment. And I was thinking about setting up my telescopes today, but I'm like, well, it's my turn to be in the control room. So I'm helping out here and doing this, but the more the merrier, as again, we've said a number of times. I hope you got that point across. The cameras can't do what our eyes can do, and each one of our setups is a little bit different. For instance, if I was imaging in hydrogen alpha, I would have been using a color camera today, so all of that you saw on Jim's telescope would have been bright red on my telescope, because that's the way your eye
Mine would
would
have
see it.
been purple, but that would...
Yeah, that purple is or in ultraviolet if people are used to seeing in ultraviolets. So anyway, folks, thank you for joining us. And this episode will be, I'll take the recording of it and it'll edit it down and put it up on our YouTube channel. So by all means, if you haven't checked it out yet, go to YouTube and search for Naperville and astronomy, and we'll be at the top of the list, I'm sure. We have a channel there. We've got at least 25 videos of the various presentations that we've done. Some of them are observing sessions, nighttime and daytime. Some of them are our indoor programs that we've been streaming all this year so far. And this will get added to it, so for people who have missed it. Otherwise, I'm going to say so long, and hope that you continue to join us in looking up and enjoying astronomy and the universe.